Let's move on to the second topic. This is about the computational efficiency. Recall that for a given computational problem, there are many programs that solve the same problem. In other words, programs that achieve the same goal. Recall also that the program is a sequence of detailed instructions for computation. But when we discuss computational efficiency, we will usually use an algorithm that is an outline of a program that may not be so detailed but still mathematically precise enough. The computational efficiency greatly depends on the quality of algorithms. In other words, computers will live or die by algorithms. Let's consider one example. Here we consider the problem of computing the sum from 1 to 100. This is our computational task or goal. We can achieve this goal by adding numbers from 1 to 100. By the way, the answer is 5050. Well, this computation needs 99 additions. But is this only the way? Here is another way. We can compute the answer by two mathematical operations. It is said that the famous mathematician Gauss thought of this method when he was assigned this task in the class when he was 7. Here is how he thought. This is what we want to compute. Consider the same sum by the reverse order. Then add each vertical pair, then we get 101 for all pairs, right? So the total sum must be 101 times 100 because there are 100 pairs. Note that this total is the double of our target sum. So dividing this by 2, we can get the answer as stated here. So by this clever method or algorithm, we can get the answer by using only 2 operations. Compared with the 99 additions, this is a super efficient algorithm. Well, this is a simple calculation task, but the difference would be significant if it were some heavy computational task. The typical situation would be the case of using a supercomputer. In this case, using efficient algorithms is crucial. Otherwise, we would end up wasting the supercomputer power. So developing efficient algorithms is quite important. Oh, good point. Yes, there is no guarantee that there is an efficient algorithm. Then we may naturally ask for which problem we can get an efficient algorithm and for which problem we cannot. What sort of problems are computationally hard? This is another important subject in the research of computation. Let me explain this. First, let us look at the trajectory of research. As we studied, mathematicians like Turing identified the basic components of computation. Then, this led the emergence of computers, which is like a big bang in the computer world. After the emergence of computers, they started to be used in many places. During the 60s, thanks to the advancement of electronics, such as the invention of transistors, integrated circuits, and so on, computers as hardware have been evolved rapidly. In parallel, computers as software systems have been evolved greatly. For example, introduction of new programming languages, discovery of various key algorithms, and development of basic software. This period was the first golden age of computers. Through this period, people have started facing hard computational problems. In so many areas of various computationally hard problems have been identified. Researchers found they could not come up with good algorithms. And over time, they started to feel there was a particular property common to those hard problems. To this somewhat vague feeling, around 1970, 2 mathematicians independently provided a sharp and mathematically precise interpretation. Stefan Cook from Canada and Leonid Levin from the Soviet Union, now Russia, well, I should call them computer scientists, or more precisely, theoretical computer scientists. Anyway, around 1970, they independently discovered some important fact, with which they clarified what researchers felt about those hard problems. Just at the time when the mathematicians were trying to define the notion of computation, and just like different people came up with essentially the same idea independently at that time, once again, mathematicians from the East and the West during the Cold War came up with each other own but similar notions. Let us look at those hard problems.